All right, 6.2 general sinusoidal graphs. Our first, or we have two essential questions. So, given a graph of a sinusoidal function, how do you find its equation? Given an equation of a sinusoidal function, how do you graph it? Okay, here's a picture of a sinusoidal function. We don't know what the equation actually is, but we have covered a few things here. One thing is a period, right? So going from, like, for example, the highest point to the next highest point. So completing one entire cycle. Like, how long does it take you to complete one entire cycle? Okay, so that's a period. The sinusoidal axis, I actually call it the midline. So that's this dotted line here. And basically, it is a transformation. So normally, this line in the like sine and cosine functions that we've explored, you've been around the x-axis, right? So you go up 1 and then down to -1, and this midline has been your x-axis. So this midline, or the sinusoidal axis, ends up wherever you have vertically translated the graph. So if you have vertically translated the cosine function 5 units up, then this midline, or the sinusoidal axis, ends up at y = 5. So the way that you find the midline is just like you would find the midpoint. Kind of think of it as all of these are like the middle of one of these branches. Okay, so the midline is 1/2 of the highest plus lowest. And those are outputs that I'm talking about. So y values. So it's really, the two, the highest and the lowest output divided by 2. Think of it like a midpoint, okay? And it shows you, this ends up giving you the vertical translation. Or the vertical translation will tell you where this midline is going to be. All right, now amplitude is a little bit different. So amplitude is how high above this midline are you and how low above the midline. It should be the same number, by the way. Okay, so amplitude is more like the distance, and it's half of the distance from like the highest point to the lowest point. So to find the distance between these two, we'd subtract them, and we only want half of it because going from the midline up or the midline down doesn't matter. Okay, and it's always going to be positive, so you're not going to think of like negative amplitude going down. When they're asking for the amplitude, they're asking how far is your highest or lowest point from this midline. So amplitude is really half of the distance from the highest and lowest outputs. So half of highest, this time minus lowest outputs. All right, so there's not a whole lot new here. When you see this, maybe the letters are different to you. But really, there's not a whole lot new. These are all the transformations that we've been talking about since Algebra 2, actually since geometry, but as far as functions go, since Algebra 2. Okay, so the absolute value of A is the amplitude. Like I said, A is not concerned with whether you're going up or down. It's just how far from this midline to the highest point or to the lowest point. And like I said, they're going to be exactly the same. Okay, so A is a vertical dilation. Okay, so A becomes your vertical dilation. That makes sense, right? It's being multiplied to this function. Okay, so this is your vertical dilation. Okay, and and we're thinking right now it's always going to be positive. It's going to be negative if the graph has been reflected over like the x-axis. Okay, so nothing new there. It's capital A. We've always used lowercase a. Okay, B is the reciprocal of the horizontal dilation. Nothing new here either, right? So B is happening to the input, right, to theta. Okay, so it's an inside transformation, and it is a horizontal dilation. And for example, in the past when we've said, all right, this graph has horizontally dilated by a factor of 2, well, really, we multiplied the inside by the reciprocal of 2, so 1/2. Okay, so B is the reciprocal of the horizontal dilation, and I'll show you how to find that in a second. C is the location of the sinusoidal axis. Okay, so we've already talked about that. That's that vertical translation. And I also call this, instead of sinusoidal axis, I call it the midline, because it's just like basically the middle of the thing. And then D is the phase displacement, or that horizontal translation, right? So we've always called that the H, and we've always called the C the K. All right, so when you're thinking about this, if you need to write yourself a note, hey, by the way, C is really K, and D is really H for us. All right, period is broadly defined as the number of degrees per cycle. And frequency, on the other hand, is the number of cycles per degree. Okay, so let's look at, we've got some properties down here. So period, you can really think of this as being 360 divided by this horizontal dilation piece, okay? So we can say that period really is the same as 360 divided by B. And we keep that positive or negative. We're going to keep the absolute value of B. If the inside of the function is negated, that's a reflection across the line or across the y-axis. Okay, so we don't really think about B and A in terms of positive and negative. We think of, if they're going to be negative, if they're going to be opposite of what they should be, then it's a reflection. This would be a reflection in the x-axis. B would be a reflection in because B is right next to the input, right? So that would be a reflection in the y-axis, okay? So you can also say then, another way of writing this is that basically the absolute value of B is equal to 360 degrees divided by the period. I think of it a lot like this because I'm trying to figure out what B is. Whereas frequency now is B divided by 360, right? You're trying to figure out how many cycles there are per degree. So it's just the reciprocal of the period. Moving on to the next page. A little review here. So we've got, in a sinusoid function, we've got, a critical point that's a max, a critical point that's a min, and so on. You have concavity, so you have concave up and concave down, and in between there's the point of inflection. What you're going to notice about these points of inflection is that they're halfway between the max and the min. So if they're halfway between the max and the min, they must be on that midline, right? So you can think of those points of inflection on that midline, or it's drawn right here, drawn on that sinusoidal axis, okay? And it's going to be, so the midline is constant where it's hitting this. It's hitting it right in the middle. The high point, they're going to keep coming out at the exact same height. The low points, those are going to keep coming out at the exact same height as well. Okay, so you always have this higher bound and this lower bound. It doesn't, and what I'm trying to say is it doesn't alternate. So for example, right now, these are not going to, you're not going to be like, oh, I'm at, 2, and then the next one, oh, I'm down here to -3. On the same sinusoidal function, you are going to be, your high points are all going to be the same output. Okay. Oh, and so what I should say about that then is that these points of inflection, they kind of break up like one period into 4 pieces. So from the high point to the point of inflection is a quarter of that period. Okay, and from the point of inflection to the low point, another quarter of that graph for that period. And then same thing here. So going from the low point back up to that midline or point of inflection, you got another quarter of the graph for that period, and then the last quarter comes from the point of inflection or from the midline to the high point. And again, a period always goes from, I like to choose like the highest point to the highest point, or the lowest point to the lowest point. Sine functions are a little bit more tricky because you're looking at, for example, the sine function goes through 0, 0. So sometimes I'll look at that. When do I get back to 0, 0? Or when do I get back to, go all the way, for example, in a sine function, go up to my highest, come back down to my lowest, and then end up back at the x-axis. So maybe that's clear. Maybe that's clear as mud. Who knows? I would like to do a problem with you, which is page 283, number 9. And I would get a few colors if I were you. And I'm going to do it a little bit differently than what your book has you do. But basically, here's what I want to do. I want to graph y equals 6 plus 5 times the cosine of 3 times theta minus 60 degrees. All right, so let's explore these things. So the first thing to remember is that this 6 here, well, that's like your A. So going back to, I'm sorry, that's like your C. I lied. So that's like your C here. Okay, so that's like what we would normally see as a K. All right, so that K, or that C, has always been a vertical translation. So I'm going up 6, which is telling me where my midline will be. Okay, it's telling me take that midline when that used to be your x-axis, shift it up 6. So really, this whole graph gets shifted up 6. Okay, now 5 is your A, so that's your vertical dilation. So what that does is that changes your amplitude. So normally our amplitude, in a cosine function, you start up at 1, your midline's down at 0, then you go down to -1. Well, our amplitude at that point is just 1. But if we take this thing and we stretch it vertically, our amplitude's going to change. Okay, so we'll look at that. We'll look more into that. All right, now we've got this 3 here. So that's our B, or that's our horizontal dilation. Okay, so this horizontal dilation is really by a third. And what that does is it changes our period. And then hopefully you're recognizing the 60 degrees in here is happening to your input. So that's what we're used to seeing as H, but now they're using D for that. So we are doing a horizontal translation. Right 60 degrees. Okay, so I am going to use a few different colors here. So it looks like we have 4 different things happening. And I'm going to also want to do the parent graph on this. let's see if I can zoom out here so that way you guys have a better view. Okay, so I am going to say, well, I know that my parent graph is y equals cosine of theta. Okay, that's my parent graph. So at this point in your life, hopefully you know the cosine graph. So on the, or for my y-intercept, I should be up at 1. At 90 degrees, I'm going to be at 0. At 180, I'm down to -1. At 270, I'm back at 0. And then 360, I'm up to +1 again. So what I've just done, I'm just dotting it. This is my parent graph. This is y equals cosine of theta. And I find it really helpful to do these in pieces. So it'll be up to you how you decide how many pieces you want to do. But this time I'm going to do every single transformation a separate color. Okay, so starting with adding 6. So right now my midline is at the x-axis. This vertical translation up 6 means that my midline is now at 6. Okay, so my midline has now transformed itself up to here. So my graph now, and I'm just going to put a pink. Okay, I'm going to do this one in pink. So my graph now is really, I'm up 1 from that midline. At 90 degrees, I'm on the graph. At 180, I'm 1 below it. At 270, I'm back on the midline. And then at 360, I'm 1 above it. So I end up with a new transform function. I'll do my best here with this pink. Oops, that's a little low. That's okay. Something like that. Okay, well, in addition to that, I've also got this vertical dilation. So let's see. How about I use a rust color? So this vertical dilation changes my amplitude. Okay, in my parent graph, my amplitude is just 1. But now I know that my vertical dilation is by 5. Okay, so instead of going from the midline up just 1, I'm going to go up 5. So 1, 2, 3, 4, 5. That's 11. Let me mark that. So from the midline, I'm going up 5. You're not going to go up from here. You're at 0, right? So if your output is 0, then you're not, well, no matter what you multiply that by, you're still going to be at 0. So this is still going to be on the midline. But my lowest point is no longer 1 below the midline. It's going to be 5 below the midline. So I'm going to end up at 1. Okay, and then what's on the midline stays. And so at 360 now, I'm up to 11. I'm 5 above that midline. Okay. Let's see. So this graph looks something like this. And I'll go ahead and highlight that 5 with, this is rust. I know you can't see that, but it's like a rusty color. Okay, next I'm going to cut everything into a third. So this cosine 3, right, this is 3 being done to what's inside. So I'm really taking a 1/3 of every single input, okay? So instead of 90, well, 1/3 of an input of 0 is still 0, okay? 1/3 of 90, though, is going to be 30. 1/3 of 80 is going to be 60. 1/3 of 270 is 90. And 1/3 of 360 is 120. Oh, did I just mess that up? I just messed that up. 90. 120. Let's see if I can get this to erase. Probably not. I was trying to be super neat. Oh, maybe. Oh, look at that. That's not bad. Okay, 120. All right, so this thing just really shrunk down to basically 1/3 of its previous size, right? So the graph now looks something like, this is still a function. I know it doesn't look like it anymore, but it is. Okay, and then the last thing we're going to do, I'll use blue for this, is now I'm going to do a horizontal translation to the right by 60 degrees. So every single input gets shifted 60 degrees over. So where this was at 0 on the x-axis, I'm now going to shift it over here, 60 degrees. My 30-degree point now gets shifted over to 90 degrees. My 60-degree point now gets shifted over to 120 degrees. My, 90 degree, add 60 to that, I go to 150. And this point up here, which was at 120, add 60, I get 180. So my final graph looks something like this. And you could, I've only sketched one period. You could keep going forever with this, okay? But this is the final graph. Y equals 6 plus 5 times the cosine of 3 times the quantity pi minus 60, or theta, theta minus 60 degrees. Okay, so it's the blue graph. That's our final one. I know I took a lot of steps here, but I wanted you to see what each and every single piece of this function does to it graphically. Moving on to example 1. Suppose a sinusoid has period 12 degrees per cycle. So your period is 12 degrees. Amplitude is 7 units. Phase displacement, that's that shift, that horizontal shift. So we can call that, I think that was D. D is -4. With respect to the parent cosine function, and we have a sinusoidal axis 5 units below. So I believe that was C. We're going to be 5 units below the theta axis. That's like your x-axis. Okay. Without using your grapher, sketch the sinusoid and then find an equation for it. Okay. Your period is 12 degrees. So that means that 12 degrees needs to be divided into 4 pieces, right? That's going to tell you where your highest point's going to go. So let me go back to this part, right? So you're trying to always take your period and divide it up into 4 pieces. That says, hey, my highest point goes here, and then 1/4 of the way, I'm going to have my midline point. Okay, and then another 1/4 of the way, I'm at my lowest point, and then another 1/4 of the way, I'm back on the midline, and another 1/4 of the way, I'm back up at my highest point. That's for cosine anyways. Okay, so if my period is 12 degrees, then that means that if I divide that into 4, then I'm going by 3 degrees on my theta axis. Let's see here. So I have to be 5 units below. But then I've got an amplitude of 7. So if actually, and then I need to shift it back 4. So I think I don't like my graph. I think I want to go back a little ways further. So I'm going to move where I have my D equals -4 and my C equals -5. I'm going to move those. And you're more than welcome to use graph paper. I'm going to do this without using graph paper. So my midline is down 5. And my amplitude is 7 from that. So from -5 up 7, I'm going to be, my highest point will be at +2. And then down 7, I'm at -12. Okay, so my midline is going to be where y equals -5. I usually put a dotted line for that. Now, again, my period is 12, so I should divide that into quarters. So I know that I need to, I need to go 3, 6, 9, 12. However, I'm going to be moving backwards or to the left 4 degrees. So I just need to make sure that, I realize where my quarters are, but I'm still going to go ahead and label everything. I think I'll go by ones. So 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 2, 3, 4. Oh, I think I'm going to need to move that a equals 7 too. That's going to be in my way. Sorry about this. I promise I was planned out, but okay. So my original cosine function, your midline is at this x-axis, you're up 1, you're down, so. But on this one, my midline has been moved to -5, and my amplitude is going to be 7. So I need to be 7 above it. So I think I'll do 2 graphs here, okay? So the first one I'm going to do without this horizontal shift. I think we can do the rest of them, okay? So without the horizontal shift, we're going to do it just thinking about my amplitude being 7, the fact that my midline is at -5, or my vertical shift was at -5. My period is then at 12 degrees, which means I have to complete one whole cycle within 12 degrees. Okay? All right, so without doing the horizontal shift, I know that my highest point is going to be 0, 2, right? That's 7 units above. Now, I'm going to break this into quarters. So I'm now on my midline at 3. I'm at my lowest point, which is 7 below -5, at 6. I'm back on the midline at 9. That's another quarter. And then I'm back up to my highest point at 12. That's my last quarter of 12. So this graph right here, I'm not going to actually highlight this too much. But this graph right here is, y equals, you got -5 plus, your amplitude was 7, cosine, we haven't found our b. We'll figure out what that is. But I did use the fact that my period was 12 of theta. No horizontal shift yet. Brings us to a good point. What is my b? Okay, well, if you remember from your notes on the previous page, which I would, this is something you'd put on your note card, b is always going to be 360 divided by your period. So I know that b will equal 360 divided by 12. Well, that means that b is 30. So I can come back over here, and instead of putting just b, I'll go ahead and I'll put 30 in there. So that's my graph without a horizontal translation. Well, my horizontal translation, I had to go left 4. So I'm going to take each one of these points, And on the x-axis or on the theta, I actually think that this is degree, so it should be the theta. And this axis will be my y-axis. We haven't been labeling that. I'm going to go back 4. So this point where I'm up at 2 needs to be shifted back to an input of -4. This point on my midline where I'm at 3, -5, I need to shift that back -4. So I'm going to be at -1, -5. My lowest point, which was where theta was equal to 6 degrees, needs to be shifted back 4, so that's going to be 2. So 2, -12 will be a point on this graph. My next midline piece, or next midline point, was at 9. That needs to be shifted back 4, so that'll be at 5. And then once again, my highest point was at 12. Shifting that back 4, I'm at 8. All right, so the actual graph, and this is just one period that I've plotted. They get kind of challenging to do the whole several periods on some of these graphs. That looks terrible, but you get the idea. So now this is y equals -5 plus 7 cosine 30 of theta plus 4, because we shifted it to the left. Okay, so my final answer here, maybe I'll put it in pink. Looks something like this. I used, and you may need to use several graphs. You might have to start with the parent cosine graph to see it. Okay, just like we did in the example before. Speaking of which, let's go back and oh, everything was already labeled first, but let's go ahead and say this was my theta axis, and then this was my y-axis. Moving on to example 2, we're going to, let's see, for the sinusoid in this figure, give the period, the frequency, the amplitude, the phase displacement, and the sinusoidal axis location. Okay. Let's start with our period. So I notice that this thing goes from its highest point, once again to its highest point, after going to its lowest point and touching that midline twice. I notice that it's from 3 to 23. So I believe that the period is 20 degrees, which then tells me that my frequency is the reciprocal of that, 1/20th of a degree. That's how long it takes for it to complete one cycle. From there, we can figure out what our B is. If we want to write the particular equation, we're going to actually need B. So B is 360 divided by the period, which is 360 divided by 20. So B gives me 18. I can find my phase displacement or my horizontal shift rather quickly. Normally, this highest point for a cosine function would be right on the y-axis, but it's been moved over 3 degrees. So that's D, that phase displacement. I know it's been moved 3 degrees to the right. My sinusoidal axis, okay, or what I like to call it is the midline. Okay, so that sinusoidal axis is C. And that's where we find the midpoint. So it's like 1/2 of the highest point, which is 56, plus the lowest point, which is -38. So you actually get 1/2 of 18, which is 9. Get on the paper here for you. And the only other thing we need to figure out is our amplitude. A couple ways you can do that. Now that you know that this is 9, then you ask yourself, well, how far is it up to 56? That ends up giving you 47. Or, like I had given you originally in the notes, it's 1/2 of the highest output minus the lowest output. Well, when you do that, you get 1/2 of, what does that give you? 494, which is 47. Okay, so a couple ways that you can think of doing that, but we're going to go ahead and keep using little formulas. That'll just make life easier for us, but you can also, once you know this, you can just say, well, 9 plus what will give me 56? I think that's all we need. So now we're going to go ahead and we're going to write our equation. So the general form for a sinusoidal using cosine would be C plus A cosine B theta minus D. Our midline, C, ended up being at 9. Our amplitude was 47. Our B we found to be 18. Theta minus, and our horizontal displacement ended up being 3. This is our final equation. How can you check it? You can graph it on your grapher and make sure that it works. Last example, example 3. Figure 6-2i shows a quarter cycle of a sinusoid. Write a particular equation and check it by plotting it on your grapher. Okay, so we've got a quarter of this. Now it looks to me like I am currently on a concave up. Okay, so my point of inflection is here, which means prior to that I was on a concave down. So sometimes it's helpful to graph these. Concave up means I'm at my, here I'm down to my lowest point. So I'm going to come back up to that midline, point of inflection, and then I'm going to go back to concave down. Right, so each of these is a quarter. I know my drawing is probably not fantastic. Some of you guys are way better at this than I am, so I encourage you to have nice, neat drawing. But we know that, basically from here, from what we were given, that piece was a quarter. Well, that piece was 7 degrees, which tells me that my period would be 7 degrees times 4, right? Because 7 degrees was a quarter of whatever this is. So my period then is 28 degrees. So going backwards, another quarter, another 7 degrees is going to be 10 degrees. Forward, 7 degrees, that's 31. And then up here, let's see, 38. We know that my midline is going to be at 8. So that's going to give me my C. Now the question is, what's my amplitude? Well, amplitude, so it looks like from 8 to 3, so that looks like my amplitude is 5. So that's pretty easy, which tells me that my highest point then should be 13. Not that that's important for putting this into an equation. The fact that my period is 28 is going to help me find my B. So B is going to be 360 divided by your period. Oh, let's see what that gives us. I think I'm going to leave it like this because I end up getting 12.857. So instead, maybe we could just reduce it. Let's see, 36 and 28 can both be divided by 4. So I get 97ths. I think that's going to be the best way to write this. All right, let's see what I'm missing here. So I got y equals c plus a cosine of b theta minus d. Phase displacement might be helpful here. So it looks like my highest point is over here at 10. So we can say that this whole thing was shifted 10 to the right. So that's going to be my D, which is 10 degrees. Now, I mean, there's a million different ways to do this. You could say it was shifted actually let's see, 40 degrees. You could say it was shifted a whole bunch of different multiples of this 10. So it's going to really be difficult when I grade these because you're all going to maybe come up with different types of equations, okay? But just to make this the simplest in my mind, I've got a period going from 10 to 28, or sorry, from 10 to 38, a period of 20 degrees, 28 degrees. So I can say, hey, originally it was up here, my highest point, and it's been shifted to the right 10 degrees. I'm going to use 97ths. And we will do this with radians as well. So it's good that you put the degrees there. That way you know what you're working with.